7.10 compounds of sulfur. Sulfur dioxide. A. Preparation. Number 1. From sulfur. Sulfur dioxide gas can be prepared by burning of sulfur in air. S plus O2 gives SO2 gaseous. Number 2. From sulfide. In the laboratory, sulfur dioxide is prepared by treating sodium sulfite with dilute sulfuric acid. Na2SO3 sodium sulfite plus H2SO4 sulfuric acid gives Na2SO4 plus H2O plus SO2. From sulfides, industrial method. Sulfur dioxide can be prepared by roasting zinc sulfide and iron pyrites. Twice ZnS solid plus 3O2 gives 2ZnO plus 2SO2. Twice ZnS plus 3O2 gives 2ZnO plus 2SO2. 4FeS2 plus 11O2 gives 2Fe2O3 plus 8SO2. 4FeS2 plus 11O2 gives 2Fe2O3 plus 8SO2. Physical properties of SO2. Sulfur dioxide is a colorless gas with a pungent smell. It is poisonous in nature. Sulfur dioxide is highly soluble in water and its solution in water is called sulfurous acid. It liquefies at room temperature under a pressure of 2 atmosphere and boils at 263 Kelvin. Chemical properties. Reaction with chlorine. Sulfur dioxide reacts with chlorine in the presence of charcoal as a catalyst to form sulfuryl chloride. SO2 plus Cl2 in the presence of charcoal gives SO2Cl2, that is sulfuryl chloride. Reaction with O2. Sulfur dioxide is oxidized by dioxygen in presence of vanadium oxide to sulfur trioxide. 2SO2 plus O2 in the presence of V2O5 gives 2SO3 gaseous. Reaction with NaOH. Sulfur dioxide readily reacts with sodium hydroxide solution to form sodium sulfide. Twice NaOH plus SO2 gives Na2SO3 plus H2O. NaOH plus SO2 gives Na2SO3. Reaction with Na2SO3. Sulfur dioxide reacts with sodium sulfide solution to form sodium hydrogen sulfide. Na2SO3 plus H2O plus SO2 gives twice NaHSO3. Reducing property. Sulfur dioxide acts as a reducing agent in the presence of moisture. Moist sulfuric dioxide reduces ferric salts into ferrous salts. Twice Fe3 plus SO2 plus 2H2O gives 2Fe2 plus SO4 2 minus plus 4H plus. Moist sulfur dioxide decolorizes acidified potassium permanganate with oxygen state 7 solution of manganese. Twice KMnO4 plus 5SO2 plus 2H2O gives K2SO4 plus twice MnSO4 plus 2H2SO4. Moist sulfur dioxide reduces halogens to halogen acids. I2 plus SO2 plus 2H2O gives H2SO4 plus twice Hi. Structure of SO2. Sulfur dioxide is angular with OSO bond angle of 119.5 degrees. The S-O double bond arises from d-pi-p-pi bonding. The S-O double bond arises from d-pi-p-pi bonding. It is a resonance hybrid of two canonical forms. Uses of sulfur dioxide in refining of petroleum and sugar, in bleaching wool and silk, as an anti-chlor disinfectant, as a preservative, in the manufacture of H2SO4, NaHSO3. Liquid SO2 is used as a solvent to dissolve a number of organic and inorganic chemicals. 7.10.2 Sulfuric acid H2SO4. Preparation. Sulfuric acid is manufactured by contact process, which involves the following 3 steps. Step 1. Sulfur or sulfide ore iron pyrites on burning or roasting in air produce sulfur dioxide. S plus O2 gives SO2. 4FeS2 plus 11O2 gives 2Fe2O3 plus 8SO2. Sulfur dioxide is oxidized catalytically with oxygen to sulfur trioxide in step 2 in the presence of V2O5 catalyst. 2SO2 plus O2 gives, in the presence of V2O5, gives 2SO3 gaseous. The reaction is exothermic and reversible, and the forward reaction leads to a decrease in volume. Therefore, low temperature and high pressure are favorable conditions for maximum yield of SO3. Step 3. Sulfur trioxide gas from the catalytic converter is absorbed in concentrated H2SO4 to produce oleum. The dilution of oleum in water gives sulfuric acid of desired concentration. SO3 plus H2SO4 gives H2S2O7, that is oleum. Now H2S2O7 plus O2 plus HO2 plus H2O gives 2H2SO4. The sulfuric acid obtained by contact process is 96 to 98% pure. Physical properties of H2SO4. Sulfuric acid is a colorless, dense, oily liquid. It has a density of 1.84 gram per centimeter cube at 298 Kelvin. It freezes at 283 Kelvin and boils at 611 Kelvin. It is highly corrosive and produces severe burns on the skin. Do you know? Sulfuric acid dissolves in water with the evaluation of a large quantity of heat. Hence, care must be taken while preparing solution of sulfuric acid from concentrated sulfuric acid. Concentrated H2SO4 must be added slowly to water with constant stirring by keeping the beaker in water bath. Chemical properties of sulfuric acid. Acidic property. Sulfuric acid ionizes in aqueous solution in 2 steps. H2SO4 plus H2O gives H3O plus HSO4 minus. HSO4 minus plus H2O gives H3O plus SO4 2 minus. The greater value of Ka means that H2SO4 is highly dissociated into H plus and HSO4 minus ions. Thus, H2SO4 is a strong acid. Reaction with metals and nonmetals. Oxidizing property. Metals and nonmetals both are oxidized by hot concentrated sulfuric acid, which itself gets reduced to SO2. Cu plus 2H2SO4 gives CuSO4 plus SO2 plus 2H2O. S plus 2H2SO4 gives 3SO2 plus 2H2O. C plus 2H2SO4 gives CO2 plus 2SO2 plus 2H2O. Remember, oxidizing properties of sulfuric acid depend on its concentration and temperature. In dilute solutions at room temperature, H2SO4 behaves like HCl, oxidizing metals that stand above hydrogen in the EMF series. Hot concentrated H2SO4 is a better oxidizing agent than dilute cold acid. It oxidizes metals like copper. Number 3. Dehydrating property. Concentrated sulfuric acid is a strong dehydrating agent. Sulfuric acid removes water from sugar and carbohydrates. Carbon left behind is called sugar charcoal and the process is called charring. C12H22O11 in the presence of concentrated H2SO4 gives 12C plus 11H2O. Reaction with salts. Concentrated sulfuric acid decomposes the salts of more volatile acids to the corresponding acid. Example: NaCl plus H2SO4 gives NaHSO4 plus HCl. KNO3 plus H2SO4 gives KHSO4 plus HNO3. CaF2 plus H2SO4 gives CaSO4 plus 2IceHF. Uses of sulfuric acid. Sulfuric acid is a very important industrial chemical. It is used in the manufacture of fertilizers, for example, ammonium sulfate, superphosphate, etc. In the manufacture of pigments, paints, and dyestuff intermediates. In petroleum refining, in detergent industry, in metallurgy for cleaning of metals, electroplating, and galvanizing. In storage batteries, as a laboratory reagent, in the manufacture of nitrocellulose products. Chlorine and compounds of chlorine. Chlorine. Chlorine was discovered by Scheele, a German-Swedish chemist, in 1774 by the action of HCl and MnO2. In 1810, Davy established its elementary nature and suggested the name chlorine on account of its color. In Greek, chloris equal to greenish yellow. Preparation. Chlorine can be prepared by the oxidation of hydrochloric acid with any of the following oxidizing agents. Manganese dioxide. Number 1, using manganese dioxide. MnO2 plus 4HCl gives MnCl2 plus Cl2 plus 2H2O. Number 2, from potassium permanganate. Twice KMnO4 plus 16HCl gives 2KCl plus 2MnCl2 plus 8H2O plus 5Cl2. Chlorine can also be prepared by the action of concentrated sulfuric acid on a mixture of sodium chloride, NaCl, and manganese dioxide. The reaction takes place in 2 steps. 4NaCl plus 4H2SO4 gives 4NaHSO4 plus 4HCl. MnO2 plus 4HCl gives MnCl2 plus 2H2O plus Cl2. That gives a total of 4NaCl plus MnO2 plus 4H2SO4 gives 4NaHSO4 plus MnCl2 plus 2H2O plus Cl2. Manufacture of chlorine. De Con's process. Chlorine is manufactured by the oxidation of hydrogen chloride gas by atmospheric oxygen in the presence of CuCl2 as a catalyst at 723 Kelvin. 4HCl plus O2 in the presence of CuCl2 gives 2Cl2 plus 2H2O. Electrolytic process. By the electrolysis of brine, concentrated NaCl solution, chlorine is liberated at the anode. NaCl reversibly gives Na plus Cl minus. Cathode reaction, 2H2O plus 2 electrons gives H2 plus twice OH minus. Na plus OH minus gives NaOH. Anode reactions, Cl minus gives Cl plus electron. Cl plus Cl gives Cl2. Physical properties of chlorine. Chlorine is a greenish yellow gas having pungent and suffocating odor. It is poisonous in nature. It can be easily liquefied into a greenish yellow liquid which boils at 293 Kelvin. It dissolves in water to give chlorine water. It is 2 to 5 times heavier than air. Chemical properties of chlorine. Number 1, reaction with metals. Chlorine reacts with metals to form chlorides. Examples: 2Al plus 3Cl2 gives twice AlCl3. 2Na plus Cl2 gives 2NaCl. 2Fe plus 3Cl2 gives 2FeCl3. Number 2, reaction with nonmetals. Chlorine reacts with nonmetals to form their chlorides. P4 plus 6Cl2 gives 4PCl3. S8 plus 4Cl2 gives 4H2Cl2. Number 3, affinity for hydrogen. Chlorine has great affinity for hydrogen. It reacts with hydrogen compounds containing hydrogen to form HCl. H2 plus Cl2 gives twice HCl. H2S plus Cl2 gives 2HCl plus S. Number 4, reaction with ammonia. Chlorine, when reacted with excess of ammonia, gives ammonium chloride and nitrogen. 8NH3 excess plus 3Cl2 gives 6NH4Cl plus N2. Excess of chlorine reacts with ammonia to give nitrogen trichloride, that is explosive. NH3 plus 3Cl2 excess gives NCl3 plus 3HCl. Number 5, reaction with alkali. Chlorine reacts with cold and dilute alkali to produce a mixture of chloride and hypochlorite. When reacted with hot concentrated alkali, chloride and chlorate are produced. Twice NaOH, cold and dilute, plus Cl2 gives NaCl plus NaOCl plus H2O. 6 NaOH plus 3Cl2, hot where NaOH is hot and concentrated, gives 5 NaCl plus NaClO3 plus 3H2O. Chlorine, when reacted with dry slaked lime, CaOH twice, gives bleaching powder, that is CaOCl twice. twice CaOH twice plus 2Cl2 gives CaOCl twice plus CaCl2 plus 2H2O. Number 6. Reaction with hydrocarbons. Chlorine reacts with saturated hydrocarbons to give substitution products, and with unsaturated hydrocarbon gives addition products. CH4 methane plus Cl2 in the presence of UV light gives CH3Cl, that is methyl chloride plus HCl. Ethene CH2 double bond CH2 plus Cl2 gives Cl-CH2-CH2-Cl 1,2 dichloroethane. Number 7. Oxidizing property. Chlorine oxidizes ferrous salts to ferric salts and sulfides to sulfates. 2FeSO4 plus H2SO4 plus Cl2 gives Fe2SO4 thrice plus 2HCl. Na2SO3 plus Cl2 plus H2O gives Na2SO4 plus 2HCl. It oxidizes sulfur dioxide to sulfur trioxide and iodine to iodate. In presence of water, they form sulfuric acid and iodic acid respectively. SO2 plus 2H2O plus Cl2 gives H2SO4 plus 2HCl. I2 plus 6H2O plus 5Cl2 gives 2HiO3 plus 10HCl. Bleaching property. Chlorine requires the presence of moisture for bleaching. It liberates nascent oxygen from water, which is responsible for its oxidizing and bleaching property. Cl2 plus H2O gives HCl plus HOCl, that is hypochlorous acid. HOCl gives HCl plus nascent oxygen. Chlorine bleaches vegetable matter or colored organic matter in the presence of moisture to colorless matter. Colored organic matter plus nascent oxygen gives colorless organic matter. Uses of chlorine. Chlorine is used for purification or sterilization of drinking water, for bleaching wood pulp required for manufacture of paper and rayon, bleaching cotton and textiles, for extraction of metals like gold and platinum, in the manufacture of dyes, drugs, and organic compounds such as CCl4, CHCl3, DDT, refrigerants, etc., in the preparation of poisonous gases such as phosgene, COCl2, tear gas, CCl3NO2, and mustard gas, Cl, CH2, CH2S, CH2, CH2Cl. Do you know? Bleaching by chlorine is permanent. It bleaches cotton fabrics, wood, pulp, litmus, etc. However, chlorine is not used to bleach delicate materials such as silk, wool, etc., as it is a strong bleaching and oxidizing agent. 7.12 Interhalogen compounds. We have seen that all halogen molecules are diatomic. They form binary components with hydrogen. With oxygen, they form oxyacids, and with halogens, they form interhalogen compounds. Although all halogens belong to same group, they have different electronegativities. Due to this difference in electronegativity, two or more halogen atoms combine to form species which may be ionic or neutral. The neutral molecules are called interhalogen compounds. For example, ClF, BrF3. An interhalogen compound is a compound formed by combination of atoms of different halogens. The interhalogen compound is regarded as the halide of the more electropositive halogen. A given halogen forms an interhalogen compound with only the halogen having lesser electronegativity. Do you know? The ions formed by combination of different halogens are called polyhalide ions or interhalogen ions. For example, K plus Cl3 minus NH4 plus I5 minus, which contain Cl3 minus and I5 minus ions. Do you know? ICl, iodine monochloride in glacial acetic acid, is called Wedge solution and is used in determination of iodine value of an oil. Classification of interhalogen compounds. Depending on their composition, interhalogen compounds are classified into 4 types. XX- example, ClF, BrF, BrCl, ICl, IBr. XX-3 thrice. ClF3, BrF3, IF3, X-5, ClF5, BrF5, IF5, X-7, IF7. In the general formula X-N, X is the halogen having larger size and is more electropositive. X- is the halogen having smaller size and more electronegativity. General characteristics of interhalogen compounds. The compound is considered as the halide of X. For example, ClF. Here, the halogen having larger size is chlorine. It is more electropositive than F, and hence the interhalogen compound is named as chlorine monofluoride. N is the number of atoms of X dash attached to X. As the ratio radius of X is to radius of X dash increases, the value of N also increases. Interhalogen compounds have even number of atoms 2, 4, 6, 8. For example, ClF3 has 4 atoms. The properties of interhalogen compounds are generally intermediate between those of halogens from which they are made. The central halogen exhibits different oxidation states in different halogen compounds. Number of X dash atoms in the compounds is always odd. They are all diamagnetic. Do you know XX dash compounds are more reactive than X2 or X2 dash? In the XX dash bond, X dash is more electronegative than X, while in X2 and X2 dash both atoms have same electronegativity. Hence, the X dash bond energy is less than the X dash X or X dash X dash bond energy. Methods of preparation of interhalogen compounds. Direct combination XX dash, both in equal volumes. Methods of preparation of interhalogen compounds. Direct combination Cl2 plus F2 in a copper vessel at 523 Kelvin gives 2ClF. I2 plus Cl2 in the presence of HCl plus HNO3 and heat gives 2ICl. Br2 plus Cl2 gives 2BrCl. XX-3 type. Cl2 plus 3F2 excess gives 2ClF3. Br2 plus 3F2 gives 2BrF3. I2 plus 3Cl2 in excess gives 2ICl3. Reaction of halogen with interhalogen compounds. Br2 plus BrF3 gives 3BrF. Br2 plus ClF3 gives 2BrF3 plus BrCl. Special reaction of ICl. I2 plus KClO3 in the presence of heat gives ICl plus KiO3. Do you know? ICl in liquid state undergoes autoionization like water to form a cation and an anion. Twice ICl reversibly gives I plus ICl2 minus. Some properties of interhalogen compounds. Reaction / property. Thermal stability XX dash type. ClF is greater than ICl, greater than IBr, greater than BrCl, greater than BrF. ClF is greater than ICl, greater than IBr, greater than BrCl, greater than BrF. Hydrolysis gives oxoacids. XX dash type. BrCl plus H2O gives HOBr plus HCl. 5ICl plus 3H2O gives HiO3 plus 5HCl plus 2I2. XX-3 type. ICl thrice plus H2O gives HiO3 plus 5HCl plus ICl. Number 3. Disproportionation / autoionization reaction. XX dash type. BrF gives 2Br2 plus BrF5. XX-3 type. 2ClF3 gives ClF2 plus ClF4 minus. ICl3 gives ICl plus Cl2. Fluorination reaction of XX-3 type. U plus ClF3 gives UF6 plus ClF. Addition across olefins. ethene CH2 double bond CH2 plus ICl gives CH2I dash CH2Cl. Uses of interhalogen compounds XX dash types. ICl is used to determine iodine value of oils as the catalyst for oxidation of astatine for preparation of polyhalides. XX-3 types for preparation of polyhalides as fluorinating agent as non-aqueous solvent.